Now we're going to talk about the relationship between work and potential energy. So let's say we have a box that's 15 kilograms, and we lift it 2 meters into the air, and we can calculate that. No forces in the x, and then if we look at our forces in the y, positive force applied upwards, and then the negative force of gravity downwards. If we lift it at a constant velocity, acceleration is 0, moving up at the same rate. Therefore, the force applied is equal to gravity, and so the force applied is 147 newtons, which is also the force of gravity. We lifted for 2 meters, right? And so we've got 147 newtons times 2 meters, 294 joules, right, is the work that we do. 294 newton meters or joules. So the question is, what is the work done by gravity? So if we do that, right, the gravity is pointing downwards and the displacement is upwards, so the angle between those is 180 degrees. So negative 294 joules of work done by gravity, right? So what is the change in potential energy? Well, we can do that, right? Potential energy is equal to mgh. We have the mass, which is 15 kilograms, acceleration due to gravity, which is 9.8, and then the height, which is 2 meters. So it turns out that we end up getting, and it's actually good, let's put it in this notation, P final, potential energy final minus potential energy initial, is the change in potential energy, right? So the final is up here, mgh, and then the initial is here. So the change in potential energy is positive 294 joules. And so that work that we did, directly translates to the change in potential energy of the system. So what we talk about when we look at this is what's called conservative work versus non-conservative work, which we're going to look at as well. So conservative work, as this goes, is equal to the change in potential energy. And in this case, the conservative work here done by, or the work done by gravity here is negative 294. The change in potential energy is positive 294. So that's where this negative comes from here. Okay. So to calculate potential energy for springs, we multiply K, which is the spring force constant, how many newtons per meter the strength of the spring is, and then X is displacement from equilibrium in meters. So if we stretch a spring or compress a spring, depending on the K value, if we have a higher K value, that means we have a stronger spring, and lower K value is lower spring. So if we stretch the spring from its equilibrium position, it's trying to pull it back to the equilibrium position. And we have a certain amount of energy. So in this case here with E8, we stretch this 6 centimeters from equilibrium, and the spring constant is 35 newtons per meter. So we want to find the elastic potential energy of the system. So when we do that, 1/2 kx squared, we have the the K value 35 newtons per meter. We have the displacement from equilibrium, which is 0.06, and if you notice, we have to have meters, right? Because we have meters here, we have to have meters here for those to cancel out. And we end up getting 0.063 joules for the energy of the spring. Okay, so now what we're going to do is draw a force extension graph for a 35 Newton per meter spring that's stretched to 0.5 meters. So we can imagine, we have the spring here, we stretch it out 0.5 meters, and part B is, how much work is done in that case. So let's go ahead and draw a graph here. We have force on the y-axis, X position on the x-axis, and if we think about, at the 0 position right here, where it's not stretched, there's no force. So we know this position is fixed, right? And then as this stretches, you know, what's happening to the force that we have here. So we know that force equals negative kx. This is Hooke's law. So you know, as we stretch the spring, it tries to restore it back to the original position. At 0.5 meters, it's trying to restore it with you know, this much force, negative 17.5 newtons. So if that's true, if, you know, as we stretch it all the way out here, it's trying to bring it back this way, we would have to apply the force the other way, you know, with 17.5. And so you know, that would be, you know, the force here at 0.5 meters would be, you know, 17.5 newtons would be how much that we need to stretch it with, and then we would get a linear graph here as we stretch it. So over, you know, the further we get from equilibrium of 0, and the closer we get to 0.5 meters, the more force it takes to do that. So if we calculated the work done to you know, extend it, what do we know about you know, force displacement graph, right? And we know work equals force times displacement. If we have force on the y-axis, position on the x, what part of the graph will help us get, you know, what we need? And if you remember from before, it's the area, right? So we get the area of this graph, and that will give us how much work it took to do that. In this case, 4.375 joules. So again, the work is how much energy it took to stretch it, and you know, we can take a look at the spring energy in this case and relate that to this, right? So you know, kx squared will end up getting the same value. So again, the work that we did, you know, to stretch this out here, we can get from this area, from the force displacement graph, and then how much energy it took to stretch it is equal to the potential energy here as we stretched it. So they all relate together.